Hi everyone, thanks for tuning in. Let's start with the big picture. Our goal is to make fuzzing on cloud PaaS platforms faster and leaner. Right now, even the best fuzzers burn through a lot of time and a lot of CPU and memory before they uncover serious bugs. We want to fix that efficiency gap so developers can find flaws sooner and spend fewer resources along the way. Fuzzing is basically stress testing software with a fire hose of unexpected inputs. We pump in thousands of random test cases, watch how the program reacts, and log every crash or hang. Each crash is a red flag that something's buggy. Because the process is automated, we can keep it running around the clock, which makes fuzzing one of the most scalable ways to uncover hidden defects. Things get trickier in the cloud. A PaaS application isn't a single binary, it's a living system that shifts across configuration states. To fuzz it properly, we have to explore that state space. Acto, an open-source fuzzer for Kubernetes operators, is one of the best tools for this job. But Acto still chooses test inputs in a fairly rigid order. That's where our work begins. We inject a dynamic seed scheduling mechanism into the fuzzer. Think of the test case pool as a deck of cards. Instead of drawing in the same fixed order, we reshuffle after every round, always placing the most promising cards on top. The reshuffle is guided by reinforcement learning logic. After each fuzzing cycle, we reward seeds that look useful and penalize seeds that aren't pulling their weight. Two signals drive that reward: crash feedback and frequency feedback. Crash feedback says, did this seed crash something, and how nasty was the crash? Frequency feedback asks, have we walked this execution path too often, or not enough? We map every custom resource definition YAML into a tree, stroll through its nodes, and pick new seed locations based on the combined score. Alpha and beta, our tunable hyperparameters, let us dial the balance between exploiting known crash hotspots and exploring fresh territory. We built all of this into an Acto add-on we call Acto Boost. The new optimizer module slots right into Acto's architecture and feeds its prioritized seed list back to the fuzzing engine. Under the hood, the rest of the system stays the same, but the order in which test cases fire is now context-aware. This is a simplified visualization of the workflow within Acto Boost. First, we select the test case with the highest reward. Then we test it on the Kubernetes cluster. After testing, we get feedback from the cluster. The oracles analyze this feedback. Using the feedback, we calculate the reward based on update frequency and crash feedback. Then again, we pick the test case with the highest reward. This process keeps repeating. That's how Acto Boost works to find bugs effectively. This is the high-level architecture of our fuzzing system. It consists of three main components: the test case generator, the optimizer, and the test case executor. The generator creates test plans from CRD schemas. These are then passed into the optimizer, which acts as the brain of the system. It processes feedback, calculates rewards, and selects the most promising seeds. Finally, the selected test cases are executed, and any crashes detected are fed back into the optimizer to refine future decisions. This loop helps the system continuously learn and improve its fuzzing efficiency over time. Tests ran on a Ubuntu VM, 48 Xeon cores, 186 GB of RAM, and a terabyte of disk. Baseline runs with vanilla Acto fuzzed 3 popular operators under 4 worker nodes. Then we repeated the experiment with Acto Boost. The payoff: Redis OCK finished 18% faster, MongoFC shaved 14.4% off, and Zookeeper trimmed almost 13%. Fewer CPU hours, same coverage, more bugs in less time. This line graph shows bug count over time for Redis OCK. Notice how 3 crashes cluster early on. That's crash feedback zooming in on a vulnerable code path. A few minutes later, 3 totally different paths get exercised because frequency feedback nudges the fuzzer toward underexplored states. We started with alpha equals 0.8 and beta equals 0.2, then tried 2 other mixes. We're still homing in on the sweet spot, but early trials confirm the trade-off is real and tunable. Let's see the demo of ActoBoost. Let's begin by showing how to start the tool. We initialize ActoBoost using a command line instruction. Under the config flag, we provide the initial custom resource definition, or CRD file. Next, we specify the number of worker threads to run. Here, it is set to 4. Finally, we define the working directory, where all logs and outputs will be saved. Once you run the command, the fuzzing process begins. You'll notice the working directory is automatically created to store all the outputs and intermediate files. After the fuzzing process completes, we can examine the generated results. Inside the working directory, you will find the trials that were executed, the test plan that guided the fuzzing, and the test logs that capture what happened during execution. Here, you can see the test plan that was used in this fuzzing session. And here are the detailed test logs recorded during the process. Now, let's move to the test results analysis. These are some filtered test cases that successfully uncovered bugs during the fuzzing. Each detected bug is stored in a dedicated directory. Within each bug directory, you'll find a file named result.json. This file provides an overview of the bug, including the time it took to detect the bug, the specific oracle that identified the issue, and additional details related to the behavior that triggered the bug. Also, each bug directory contains all the mutated YAML files and the system states recorded after each mutation. This helps us trace back exactly how and when the bug was introduced. That concludes the demo of ActoBoost. Where next? First, we'll generalize the approach beyond Kubernetes to any state space-heavy platform. Second, we'll automate hyperparameter tuning to squeeze out even more efficiency. In short, ActoBoost brings dynamic seed scheduling to stateful PaaS fuzzing, prioritizing inputs with crash and frequency feedback, and, in our tests, outpacing vanilla Acto every time. This is end of our video. Thanks for watching, and we're excited to share the code and results with the community.